Hey, good morning, everyone. First, I would like to apologize for the last week's sudden absence. It was not planned. I'll make sure that this doesn't happen next time. And if there is anything, I'll try my best to post it on my times beforehand, okay? So your time is not wasted. With this, we'll start today's lecture. Sequences and mathematical induction. So let's first go through. We will look at different what sequences are, what are its components, and we will look at some different types of sequences. And this information you need to know because they will be used in mathematical induction. Mathematical induction is one of the ways to prove different formulas for sequences, general formulas or explicit formulas, and for theorems, for some properties, laws. So we use mathematical induction is one of the ways to prove the statements, just like your direct proof and then counter examples to disprove some given statements. And also another method that we will use, which is proof by contradiction. So let's first look at sequences, the definition and its main components, and then we will look at different types of sequences. Okay, we'll first go through a scenario. For example, let's say you want to count your ancestors, previous generations. Okay, I'll go through this. This is from the book. Please refer to the book when you are studying. Let's say you want to count your ancestors and you have two parents. So from both sides you have grandparents and then their grandparents, and so you want to count all of those. So you start from two parents, one, okay, your father and mother, and from there you have two parents each, and then two parents each, like this, okay? So this gives you a certain type of sequence if we write it in the form of terms. So this means your parents and then their parents, pair of each, and then their, okay? So this is called sequence. Okay, this is a very common example of sequence, and each sequence has some sort of pattern in it, a constant pattern that repeats over time. Okay, so that is known as a sequence, and there is a position for each term in the sequence. Each of these values, these are known as terms. So each of these have their own position. So let's say if we look at the same sequence that I just talked about, for example, this first term is at position 1. In your data structures and algorithms, you will have, you will start your position from 0. Okay, so it's similar to that. So then second term, it's at position 2. Third term, it's at position 3. Fourth term, it's at position 4. So and so on. So how can we write it? For example, the first term, we can write it as 2 to the power 1, okay, because it's at position 1. And then second one, the number corresponding to position 2, the same thing, this position corresponding to that, the term is 4. Sorry. So it gives us something like this. It gives us a pattern. We try to find a constant pattern, means the pattern that repeats in the terms that are included in the sequence, and based on that everything else follows, means we try to find the explicit formula or the closed formula or general formula, and then we have some established formulas based on the patterns, just like in your previous classes. Please, this murmuring is interfering with my whatever I'm speaking. Okay. So in last week's lectures, we talked about something called, we take a value which is arbitrarily chosen, okay, and then we apply some formula because it should be applicable. For example, the definition of even integers and odd integers, we can pick any number and then plug that in to find out or to provide or write a proof for that. Similarly, over here, we try to find a pattern that repeats in a sequence, and based on that, we design or we develop a closed formula or general formula or explicit formula, same thing, okay? So, formal definition of sequence is, a sequence, it's a function whose domain is either all the integers between two given integers or all the integers greater than or equal to a given integer. So in discrete mathematics, this also I want to tell you that we have two different types of mathematics. One is continuous and second is discrete. In continuous, it's like when you have real numbers, you have 1, and in between 1 and 2, you have all the different values. We deal with all of them. One of the field of study that falls in this category is calculus. And in discrete, we deal with integers. It's like, steps. When we step on the first stair, we cannot, the second one is step 2. It's not like 1.5 or 1 point something, right? So we deal with these type of numbers. That is why we deal with integers, because they are whole numbers, okay? So mostly we deal with integers in discrete structure. So you will find this type of numbers in most of the topics that are included in your discrete structures, okay? So a sequence is a function whose domain is either all the integers that fall between two given integers or greater than or equal to a given integer. We will look at an example of that later. So how do we symbolically represent a sequence? For example, we saw the sequence 2, 4, 8 and 16 for the calculation of ancestors. So what is the general representation of that? We take it as, let's say, this one. This is our first term. How do we read it? I'll show you that later. This is third term, fourth term, and so on. Okay, up to nth term, which is the final term, or you can say upper limit. Okay, this is known as upper limit or the final term, and this is known as initial value or lower limit. Okay, so remember this. Each individual element is known as, how do we represent it? With k. This you should be familiar from your previous lectures. K is any m, any value. Okay, so general variable we use is k. You can use any other, but this means that it is any value. Okay, and how do we read it? We read it as a sub k, or a sub k for now, we'll stick with that. A sub k, and this is your one term in a given sequence. Okay, this k is known as a subscript or an index. Okay, that is why a sub k is from subscript. Okay, and this I have already told you that a sub m is where m is the subscript of the initial term, means the first one, and a sub n is where n is the subscript of or index of the final term or the upper limit. And when we have something like this, it means it is an infinite sequence. Okay, usually we deal with some enclosed sequence, some values, some first terms of some sequence. That is why we always have at the end something like this. We don't leave it at that. We don't deal with infinite sequences. We deal with mostly there is some final term or upper limit involved. It could be n plus 1, n minus 1, or whatever given. It depends on the question that is given to you. And for each sequence, we have, for some important ones, some well-known sequences, we have explicit formulas, already established explicit formulas, and we can also find explicit formulas from pre-established formulas, explicit formulas, okay? We'll look at examples of these later on. Okay, let's look at there are different ways, just like your previous lectures, there are different ways of asking questions in each topic. You could be asked a question in different ways, so you should know all of those in order to answer your in your midterm and also your final exam. So one type of question you could have is define sequences A1, A2, A sub 1, A sub 2, A sub 3, and so on. And second sequence is B sub 2, B sub 3, B sub 4, and so on by the following explicit formula. So this is the explicit So this is the explicit, this is first explicit formula, which is for first sequence, and this is second explicit formula, which is for second sequence. And initial value is always given to you, okay? If it is not given to you, it means you should know what will be the initial value. We are dealing with integers, we are dealing with positive integers, so smallest positive integer is 1. If in a statement or in a question, initial value or smallest value is not given to you, what does it mean? It means that you have to look at the smallest positive integer, because we will be dealing with positive integers, okay? So, but usually they are given to you. For example, in the first one, the initial value is 1, and in the second one, initial value is 2, okay? You just have to plug those values in here, and then the type of question you could have is compute the first 5 terms of both sequences, okay? So if we look at the first one, first explicit formula, it is k over k plus 1, and you are asked to find out first 5 terms in a given sequence, this one, using this formula. And the smallest value of k is also given to you, which is k is greater than or equal to 1, means 1 is included. So your first term will be this. Second term will be the one after it, 2. Everything else will remain same, just substitute k with 1, 2, 3, 4, 5, okay? Wherever, starting from whatever your initial value is, and so on. And then third will be 3 over 3 plus 1. What will be the fourth one? Yeah, and you have to find 5, so next one last will be 5 over. So this is how you can compute it's a very simple example of how to compute the first few terms based on the information given to you. What type of information is given to you? You are given explicit formula and you are given the smallest value or the initial value. From there you start. For example, here let's say the smallest value was, and you had to find first 6 terms using this formula. So what will be your first value of k in this formula? What will be that? Yeah. And then so on. This is first term, then second, third, fourth, just plug in the values. Okay. So this is one of the common types of questions in sequences. And then here you have the answers for that. Same applies to second one. You just have to substitute values of I starting from the smallest and plug those in until you find first 5 terms. Okay, and then you will see the pattern. You will be able to note the pattern, which will tell you why you have the explicit formula for this sequence, because the pattern is repeating in the sequence. If it is not repeating, then you cannot have explicit formula. Okay, because explicit formula or general formula is for any integer, any given integer, it is applicable. You should be able to find out value for any given term, or you should be able to find out any given term given the formula. Okay, so that is why the formula should be general and the pattern should be consistent throughout the sequence. Another example of a sequence is, for example, the first one was powers of 2. This one. This was for the ancestor one, the one with 2, for the very first one, 2, 4, 8, and so on. So here this was the pattern. Here we have another, just to show you an example. You have a formula for a sequence such that when you plug in the values, you will get alternating values. That is why it is known as alternating sequence. For example, and this is also a general formula. And here smallest value is 0. So when you plug in first 4 or 5 values of j starting from 0, you will start to see the pattern. For example, this will be your first term, this will be second term, third term, fourth, fifth, and and so on. When you compute these, when any base has power 0 in its exponent or power 0, we consider it as 1. Okay, in discrete math. In some other mathematical aspects, we consider it as 0, but in discrete math, we will consider wherever we have power 0, we will take that as 1. Okay, this will also be applicable when we discuss factorials. So remember this. Then, what will be the answer for this? -1. Then, yeah. So you see pattern of 1, -1, 1, -1. That is why this is known as alternating sequence. So depending on the type of pattern we have different types of sequences. We have sum of first few integers, then we have sum of geometric sequence, then we have Fibonacci series. All these are sequences already established. They have their own general formulas, because the pattern in the terms, it repeats. Okay, it is consistent. It consistently repeats. It is consistent. Okay. So here, if you see, this is an example of alternating sequence, and we can also find explicit formula given that we have some initial terms to identify pattern. Okay. For example, here, if you see, what type of pattern can you identify over here? Anybody? Yeah. Before that, like in simple terms, what do you notice in these terms? Sorry? Yeah, it does, but you see, you have an alternating sequence of -1 and 1 in the numerator. Okay, and then if you look at the denominator, you have what? Perfect squares, right? So you can write it as something like this. Then you can further refine it. For example, if you look at over here, so this is your first term. You have perfect square in the denominator, and then you have alternating sequence of 1 and minus 1. Based on that, you can write down the general formula. For example, over here, plus 1 minus 1, k square. You can further refine it, this formula. If you look at, further look into it, wherever you have positive 1, see what type of number you have in the denominator. Perfect square of odd integers, right? And wherever you have minus 1 in the denominator of that numerator, you have perfect square of even integers. Okay? So what you can do is that you can further refine it in this way. See, minus 1. But you can, for the scope of this lecture, you can stop here also. This is also acceptable. But because this is an established formula, I am showing you complete steps. So if you further refine it, this will be your general formula for the sequence of alternating 1 and minus 1 in the numerator and perfect squares in the denominators. Okay. So this is how the purpose of showing you this is that you have to first find out if you have ratios or if you have any other types of numbers. You have to look. You have to first look simply. Look what type of pattern is there. If you have numerator and denominator over there, what is the pattern in individually in both of those? Is there a relation between numerator and denominator? For example, if the numerator is increasing with consistent value, is the denominator also increasing with consistent value? You can look into that. Is there any other relationship between those two numbers? Let's say you have a ratio in that case. Just one example similar to this one. For example, this one here, first you identified in the numerator that it was an alternating sequence. Pattern was repeating 1 minus 1. Okay, alternating sequence of positive and negative 1. Then you focused on what is in the denominator, what type of pattern is being repeated. Okay, then you tried to find a link between these two. So, for example, wherever the same steps that I told you, wherever you have 1, you have positive there. Look into at least 4 or 5 terms if the pattern is being repeated or not. Okay, just don't stop at 2, 1 or 2. You have to look into at least 4 or 5 terms to find out, to determine that a pattern is being repeated. Okay, so based on that, you find the explicit formula, and then you can further refine it so that whenever you plug in any integer from a series, from that series, any integer, you can find out the term, okay, of that sequence. Okay, that is how the explicit formulas are established. So what we have covered is what sequence is, different types of sequences we have, what are its components, and then how to compute the first few terms of a given sequence, given that you have the explicit formula and you have the initial value or the smallest value, and then how to find out explicit formula for a given sequence. Then we will look at 2 types of notations, summation and product. Summation notation is, let's say, this is from your first slide, the representation of a sequence. And I will go through this. Consider the example in which a sub k is equal to 2 to the power of k. It represents the number of ancestors a person has in the kth generation. What is the total number of, now when we are moving one step forward, now when you want to find out the total number of ancestors for the past few generations, how can you find that out? You simply add them up, right? So that is your summation. How do you represent that summation? This is the notation for that, symbol for that. Here you have the lower limit. Whatever is mentioned below this summation is the lower limit or the initial value. Whatever is above this notation is known as upper limit or the final term. okay, value. And then here you have some mathematical expressions. Based on that, you plug in, you start from this initial value, plug that in, whatever mathematical expression is given to you over here, and then you continue until you reach the upper limit. Okay, so that is how you can find out, for example, for a given sequence, if you want to find out total number of ancestors, if you want to find out sum of some terms in Fibonacci sequence, or whatever it is, sum of some first few terms in the sequence of integers, geometric sequence, whatever that is. Okay, so you can simply add them up. This is the formal explanation of summation notation. I'll go through that for you. If m and n are integers and m is less than or equal to n, we are talking about upper and lower limits here, the symbol, this summation notation, k is equal to m, here m is the initial lower limit, and n is the upper limit, and this m is less than or equal to n, okay, always, and it is read as the summation from k equals m to n of a sub k. Simply you are reading this summation notation. It is the sum of all the terms starting from a of, what is the lower limit? M. A of m, okay, then plus 1. You have shown some terms over here up to a of whatever is in the upper limit, a of n. Okay, it gives you the sequence. So this is the expanded form of any summation notation. Okay. So here what you have to remember is what lower limit is, what upper limit is. You start from the lower limit, and from there you reach the upper limit. You show all the terms, plug in the values starting from the lower, reaching till the upper. And the second thing that you have to remember is that m means the lower limit is always less than or equal to n, means the upper limit. Okay, these two things you have to remember. Here are some examples for you to for your practice. Now again, pay attention to the type of questions. Let a sub 1 equals to minus 2, a sub 2 equals minus 1, a sub 3 equals 0, all the values for the terms are given to you, and then you have to compute the following. First one, here lower limit is, or initial value is 1, upper limit is, or final value is 5, and then the expression that you have is a of k. Now what you have to do is compute, you have to compute this. How will you compute it? Yeah, so you started from the lower limit and consecutive integers, plug those, reach till the final, and then simply here the values are given to you, just have to plug in those values. What about second one, this one? What will be the value for this? Yeah, that's it, because yeah, and then from the question check what is the value for that, minus 1. So okay, so this is how, this is to show you how to from where to start and where to end. Okay, and then how to compute. Sometimes these are not given to you. This is like one of those type of initial type of questions, that simple type of questions, sorry, that the values for these are given to you. Otherwise you have to compute them yourself. Okay, for example here, now you have to compute, only this summation is given to you, so you have to find out. So what will be the terms for this? Okay, instead of k, you will take the smallest value, which is 1. Yeah. Okay, so two types of questions, where the values for this expression is given to you and where they are not given to you. There you have to look at these lower limit and upper limit, and just add those, plug the value of k and then add them up. Okay, so then you can compute, and whatever answer you get, you can write it over here. Okay, so first type of question, two types of questions we have covered. Now next one is, how to write this down in its expanded form. Okay, so now here nothing is given to you. You don't have you don't have to find some specific terms or first few terms. You have to write down the generic sequence for this. So first initial value will be the same. You will start from the lower limit, plug that in this expression. Wherever you have I, plug it. Then after that, you can write down 4 to 5 first terms, and then because you don't have any particular integer given to you, so this will be, n will be your final term. So let's first write down 2 more terms for this. So after this you will have this one, then you will have this, and then, oh sorry, not this, this, plus. Now wherever you have I, you will replace it with the final or the upper limit, which will be n. Okay, so this will be your final term in this case. Okay, this is how these are three types of questions in summation notations that you can expect. First one is both the things are given to you. Expression is given to you, lower limit, upper limit is given to you, values for the expression is also given to you. Simply have to plug those in. Then second type of question, the values for the mathematical expression are not given to you, but you are given the lower and upper limit. You have to calculate them yourself. Okay, so you should know that in summation what you have to do, in product what you have to do. Sometimes it's very simple, but sometimes students they get confused between sum and product. So remember, this is for summation, this is addition. Okay, and third type of question is that you simply have to write a given summation in its expanded form, where you don't have the specific final term. The integer for that, integer value for that is not given to you. In that case, what you can do is show up to 3 to 4 or 4 to 5 first terms, and then just write down plus, and then in between whatever you have, you can simply show that as these ellipses, and then you can simply replace every I with n. Okay, lower limit with n in as your final term. Okay, these are some examples from your summation. Then you have product notation. Here you use this pi, capital Pi, to represent or represent this product of integers or product of given expressions. It's the same as your summation, just that here you will be multiplying the terms. Okay, everything else is same. Your lower limit is the same. Lower limit will be less than or equal to the upper limit, or you can say upper limit will be greater than or equal to the lower limit, same thing. And everything else will remain the same. Only the only difference will be that you will be multiplying the terms, whatever those terms are. And this is the general representation of terms in a given sequence. This is the final term, this is the initial term. Here you have some examples. Okay, let's solve this simple example. What will be the answer for this? You have to compute the following products. So, simple, right? Okay, this one. Okay, because this lower limit is the same as upper limit, so you need to find only one term. All right, clear? Just okay. Now next we have some 3 properties of summations and products. Some of them are based, most of them are based on algebraic laws. Okay. First one is for 2 of these. First one is for summation. Second one is for a mix of summation and product. And then third one is for product. Okay, I'll go through it. If A sub m, this sequence A sub m plus 1, A sub m plus 2, this is your first sequence, and second sequence is B of m plus 1, m plus 2. These are 2 sequences of real numbers. Now we are looking at real numbers. And C is any real number. Okay, so we are defining the terms before whatever we are going to deal with in the properties. Then the following equations hold for any integer where n is greater than or equal to m, means the upper limit is greater than or equal to lower limit. Okay. First one is that when you have 2 separate notations, 2 separate summations, you can simply take their terms and add them up. It will give you the same answer. Okay. So let's say you have 2 sequences, and for both of the sequences you have separate summations. What you can do is you can simply take their values, I mean the expression, whatever that is, and add them up. It will give you same thing. The answer will be same. Okay. So this is your first property. Next one is for when you have a real number and it is multiplied with some summation, you can simply bring that real number within the summation and multiply. After calculating all the summations, you can multiply it with this number. It's similar to this. For example, you have a sequence of 2 plus 4 plus 8 plus let's say this is the sequence. Okay, you got this as a result of some expression, and you have some real number, let's say 1.5. Okay, it will give you the same answer. Okay, so this is simple representation of this. This is distributive law, based on distributive law. Okay, so any real number, if it is outside the summation, you can simply bring it inside the summation. Calculate the sum of the numbers, the integers, and then multiply it with your real number. It will give you same answer. This is second property. And third one is same as the first one, just that it is for products, product of numbers. Okay, so if you have 2 sequences and you have to you are given the product of both of them separately, you can simply combine them in one pi or product or whatever that notation is, and multiply these. Okay, these terms. It will give you the same answer. This is the third property. First for summation, third for product, second one is for summation with a real number. Okay, so remember like this. You can remember the keywords for properties. Is it clear? Clear? Okay. Here we have some examples. So let A sub k equals k plus 1 and B sub k equals k minus 1 for every integer k. Write each of the following expressions as a single summation or product. So first one is, remember your 3 properties. So what do you observe over here? How can you write it as a single summation? You have two summations. Here you have a real number. So you can use two properties over here to simplify. Second property over here. So second property of summation you can use over here. I will erase this to here. Okay. What is that property? Sorry about this. Okay, so you can, if you look at the second summation, you have a real number over here. This here you can apply the second property, bring the real number inside, and then simply this one. Okay. Okay. And then what you can do is, either you can write it like this or it's up to you. For the second one, third property, what is that? Yes? Yeah, like this. And then in the question, the expressions are also given to you for each of these, for each of the sequence. Okay, you can say kind of formula is also given to you. So simply substitute those formulas. A sub k equals k plus 1, so it will be k plus 1, and then it's a product. So for b sub k, it's k minus 1 given in the question, and here you will have your product notation. Is it clear? Yeah. This is just the application of properties. Yeah. You just simplify this notation using the properties. So it's not like it's not a question that you have to answer, plug in the values and everything. Whatever is given to you in the question, that you have to keep in mind. Second, you have to remember the properties, and based on that, you have to simplify. Okay? Yeah. Yeah, you can say. Just application of properties. Okay? But if, for example, I think there are questions also. What happened? Sorry, there is some issue with this screen. I don't know what's the problem. I'll just use these slides. I don't know what's the problem with the other one. Okay. So we were on the properties of summation and product. Then application of properties to simplify given summation and product notations. And then lastly, yeah, we were here. Okay. So this is simplification and how to use these properties. So this one is just the solution of whatever I have told you for this one. For slide number 27, the solution is given to you in slide 28 and 29. Okay, so you are simply plugging in. Okay, they have first substituted the values given to you in the question. Doesn't matter, it's okay, and then you have applied the properties. So wherever you see theorem 5.1.1, that is actually, this is the first property of summation. This is the second property where you have the real number, and you can refer to book for that also for that. And but I have included them in your slides. And for the second question, you are applying the third property, which is for product notation. So here it is mentioned. Okay, and then you can simplify. If you can simplify, you don't need to solve. Okay, when you are applying the properties. Is it clear? Clear all these summation? Yeah. This one you have to see with what summation it is attached to. Yeah. No, it is with b sub k. See this one. This is the second. The real number is with the second notation. My solution. Oh, the one that I wrote, because I didn't see the slide, so you have to look at this one. Yeah, just when the solution is given to you, because we switched the slides, so look at the solution that is given to you over here. Okay, yeah. So whatever you wherever you have the real number, it will stay with that. Okay, like this one, and after that you apply your first property. And then you can simplify. After that, you have last one. This is the last one in your sequences. So factorial. Who knows what factorial is? Yeah. Yes. Yes. Sorry, I thought you had a question. So yeah. Oh yeah. Yes. That depends on the type of question given to you. In some, generally speaking, if you look at questions from your last lecture, in some of them you had to plug in the values. For example, when you have to disprove a statement, you have to show it through a counterexample, right? There you will have to plug in the value. But when you are showing the proof, direct proof for something, you have to show it in terms of whatever you are saying, in terms of general representations or general terms. Yeah. So it depends on the question. Oh, there we will use mathematical induction. Yeah. Yes. This is like a base for you, or these all of these will somehow be used in your mathematical induction. That is why I'm introducing these to you. Yeah. Okay. Okay. All right. So last thing for in your sequences is factorial. So factorial is the same as what the student has told, that for each positive integer, factorial is for your positive integers. For each positive integer n, the quantity n factorial, which is denoted as n and then exclamation mark, it is defined to be the product of all integers from 1 to n. So all the, for example, you have 7 integer and you want to find its factorial. You will take all the preceding integer and take the product of that until 1. Okay, so that gives you factorial. Okay, for example, and how do you represent it? For example, I don't know if I can use a pen over here. Okay. So this is your, how do you represent it? This is n factorial. Okay, what it is in terms of, first let's look at it in terms of some positive integer. Let's say you have to find out 7 factorial, means factorial of 7. What you will do is multiply it with all preceding integers till 1. Okay, this will give you factorial of 7. Now how do you, this is like 1 term, 2nd term, 3rd term, 4th term. If this is n, then what is this? What is this? And up to 1. Okay, so this is the general representation. And from here you can get a recursive definition which will help you in finding the explicit formulas for some given some additional sequences. Okay, so for what that is, this is the recursive definition. For when you have 0 factorial, the value will be 1. Okay, so it will always be 1. So that is why you have, if n is equal to 0, it will be 1. Otherwise you can write it as, pay attention to this one, n and then n minus 1 factorial. It's the same thing as n factorial. Okay, just a different way of representing. Okay, so because you will have applications of these when you want to find out explicit formula, or there are some other applications also. And this is, here the initial value will be 1. N is greater than or equal to 1, because for 0 you already have a pre-established value, predetermined value. Okay, so 0 factorial is 1, and for all others you can use this, or you can use this. Both of these are same. Here in this case n is greater than or equal to 1. Okay, so this is your concept of factorial. Now here you have some examples of how to find out factorials, the values. So this is pretty simple. Yes, what will be the answer? Product. And there is another way based on the recursive definition. You can write it as this, right? You can write this as this, right? You can separate the first term, and then can you do that? Right? Similarly for this one, n plus 1 n factorial, how else can you write it? can separate the first term and then, right? N factorial, and then this can be cancelled. You are left with n plus 1. Okay, so this is the application of your recursive definition of factorial. This one, the one we discussed here, this one. Okay, is it clear? Clear? Yes? No? Then factorials are also used in a later topic that we will study in your counting, permutations and combinations. So we will look at a very starting point of that, n choose r. This notation, this is, here we use a factorial, and also you will find it in your assignment also, wherever you have the application in the task where you have application of counting concepts including permutations and combinations. There you will find the application of factorial. For example, there are different ways of writing n choose r. One is this, then n choose r, or you can also write it as n choose r, or there are different other ways also, like this. What this is, here there is a formula called, where you have the application of factorial. The formula for this is, for combination, it is n factorial into n minus r. You will find it in your assignment. Okay, so remember, more we will study about this in your counting later on, after your midterm. So here you have, just to show you that there is an application of factorial in combination and permutation formulas, and how do you read it, n choose r. And usually the value of n is greater than r. Okay, so just remember these points. We will look into these in more detail in your counting chapter. Okay, so this is what it is telling you, that r is greater than or equal to 0, means it can be 0 or greater than that, and it is less than n. Less than or equal to. Okay, with all this as a base, we will now look at what mathematical induction is. Mathematical induction, to tell you simply, it's just a way of proving statements, theorems, formulas. Okay, and there are steps, just like in your direct proof. For example, a statement or a universal conditional statement is given to you and you're asked to prove it. There you have, it has its own steps. For example, you have to consider the hypothesis, you have to assume it to be true, and then the proof you have to show for what? For the conclusion part, right? You start from the hypothesis, plug in the values of whatever integers are there in the conclusion, and from there you show your proof for the conclusion. Similarly, in mathematical induction, you also you have 2 or 3 steps that you have to show. So first we will look at what principle of mathematical induction is, and what method of proof of mathematical induction is. So this, I hope all of you are familiar with this one, this notation now. It's the predicate or the function or the property. Okay, let P of n be a property that is defined for integers. All of this is from your logic of quantified statements. Okay, so that is your base, and let A be a fixed integer. Now you have to remember 2 things, P of n and fixed integer. Okay, these will form the base of your mathematical induction. Suppose the following 2 statements are true. P of A is true, means this property is true for some fixed integer A. Then for every integer which is greater than, which you can represent as k, which is greater than or equal to A, if P of k is true, then P of k plus 1 is true. So you have 3 things. You have actually 4 things. You have P of n, this is any property, and then you have second statement that this property is true for any fixed integer, and then you assume that it is also true for any given integer which is greater than or equal to a, and then it is also true for the integer after this. Okay, so you assume this to be true and you show the proof for this one to be true. You show the proof for next term. In your universal conditional statements, what you do is that you assume the hypothesis to be true and you show the proof for the conclusion. In your mathematical induction, you assume that you first show the proof for some fixed integer, then you assume that it is true, this property is any property, whatever that property is, it is given to you in the question. You assume that it is true for any arbitrarily chosen integer k which is greater than or equal to the fixed integer, and then you show the proof for the next one, k plus 1. Okay, let's look at it, how to actually implement it. It's the same thing, whatever I have told you just now, it's the same thing which is mentioned in your slide 38. I will show you through some example. Let's say you have a sequence is given to you and its explicit formula is given to you and initial value is given to you of the integer, and you have to prove it using mathematical induction. You have to show 2 steps. First one is your basis or base step. Here you will show this will be p of n. Okay, this one. Okay. Now in the basis you will prove p of a. What that will be? This a will be whatever initial value is given to you in the question. Okay. So in this case you have to prove this p of n to be true for the smallest positive integer, which is 1. So what you will do is, wherever you have left hand side, you have right hand side, wherever you have n, you will replace it with the smallest value, whatever that is. It's 1, 2, 0, whatever that is. Okay. In basis step, this one you will simply replace with n with whatever value is given to you on both sides. You can write them down side by side, or you can show them separately, the left hand side and right hand side. Only when you show the basis step to be true can you move forward to the next step, which you have to show in mathematical induction. So this is your first step of in proving statements or sequences, and it's their given explicit formula using mathematical induction. Now this was your left hand side. On right hand side, wherever you have n, replace it with the smallest value given to you or initial value given to you. And simplify, the answer you will get is 1, because 2 by 2 is 1. So this you have proved p of a to be true. Okay, so a was some fixed integer which was your initial value. You have proved it to be true. This is the first step that you have to show. Basis or base, whatever you call it, it's the same thing. Okay, so after that, second step is induction step. Here you have to show 2 things. I told you about principle of mathematical induction. You identify p of n, then you show the statement to be true for some fixed integer p of a. After that you assume p of k to be true, then you show proof for p of k plus 1. So in your induction you will first assume, this step will remain the same in all the questions. You will assume p of k to be true. Okay, it will always be, you will assume it to be true. What you will do actually in this step is you will look at p of n, replace every n with k, and you will assume it to be true. For example, in this question, you are done with the first step. Second step is your induction. Here, first thing that you have to show is that p of k, you have to assume it to be true. In this, what you do is you take the whole sequence and the explicit formula, both sides, wherever you find n, replace it with k. Both on your left hand side and right hand side. This is known as inductive hypothesis. You assume it to be true. Now this will be your one way to show the proof is that you use this as your starting point to show the proof. Okay, so this is the first thing in the induction step. Second step is prove. What you have to prove? P of k plus 1, the next term. This is what you have to show the proof for. Okay, in this step what you actually do is, on the where you have the explicit formula, there wherever you have k, you replace it with k plus 1. On your sequence side, means left hand side, you can show it in two different ways. One is this here, but you have to be careful over here. What does this mean? What does this include? This includes k also, because before k plus 1 you have k. Okay, so either you can simply show it like this, keeping in mind that this includes k. Okay, so you are adding k plus 1 after k, because the term after k is k plus 1. Okay, or you can simply show it like that, so to not get confused. Okay, so write down the whole sequence from your inductive hypothesis and add k plus 1 over there. Okay, and after this, another important step is, from your inductive hypothesis you know that 1 plus 2 plus 3 plus ... plus k is equal to this formula, right? So you can substitute this whole part with the right hand side, right, to simplify it. So simply except for k plus 1, replace everything from the inductive hypothesis. Let me show it to you. Let me show it to you over here. Okay, so induction step, this is the second step. First thing is you assume P of k to be true. Here you have your sequence. Wherever you have n, you replace it with k on both sides. And this is your inductive hypothesis. Mark it, because you will be using this in your proving part. So next what you have to prove is P of k plus 1. So this is the part that you have to show the proof of. What you do over here is look at your inductive hypothesis. This is the inductive hypothesis. Replace on the right hand side every k with k plus 1. It will be k plus 1 plus 1, so k plus 2. Okay, this. And then you know that from the inductive hypothesis this whole sequence is equal to this formula, right? So you can substitute it over here. From the inductive hypothesis, and then bring this k plus 1 down as it is, because you are showing the proof for that. And on your right hand side you can simplify it mathematically. Now here onward, from here it's up to your mathematical capability, how you show that these two sides are, left hand side is equal to right hand side. Here you have to use your mathematical knowledge from high school. You have to use, you just have to show that left hand side is equal to right hand side. Okay, so important steps are these: your inductive hypothesis, then replacing or substituting, no, replacing every k with k plus 1 on the right hand side where you have the explicit formula. On the sequence side, you add k plus 1. And after that, you substitute the sequence from the inductive hypothesis with the formula. And these two are important steps. After that, it's up to you how you show left hand side is equal to right hand side. Okay? You just have to, the same as your base step, you have to show that left hand side is equal to right hand side. Okay? For example, here you can take same denominator. Okay. It is equal to this. I am solving left hand side, so this is equal to k square plus 3k plus 2 over 2. This is the left hand side, and when you multiply these two, you get the same answer. Okay, and this will be your proof. This is one method. Does it make sense? Is it making sense? How to show the proof? Yes? Okay. So this is one method. Next method is, this was for sum of first few integers. Then you have, next example is, all of this I have given to you from the book also. You have all the explanation for each step, and you can refer to the book on page 280 and 281, chapter 5, to understand if you want to, for your self-study also. But it's the same thing as I have shown you in the proof. Okay. This was for the sum of first n integers, the proof for that. Then another example where you can use mathematical induction is your, we have application also, we will look at that later. Sum of a geometric sequence. Here, sum of a geometric sequence is given to you through this. You have summation notation, sum of geometric sequence, and then you have explicit formula for that. Now here you need to know a few things. How I will go through it for you to understand. In a geometric sequence, each term means this term, each term, this is your term, okay, general representation. How it is obtained? By it is obtained from the preceding one by multiplying with a constant factor, and that constant factor is represented with r variable. Okay, and here first term must be 1. Okay, so this, it depends on the type of sequence you have. For example, in your Fibonacci sequence, you need to have, I think, 0 and then 1, and then you have other values. Okay, so similarly in your you must have some initial values, they need to be there. Okay, so similarly in your geometric sequence, 1 needs to be there, and then you have how you show the sequence. 1 r, this means r doesn't matter, when there is nothing it means there is in the power it's 1, and then you have r square, r cube, and up to rn. This is the geometric sequence, and when you take its sum, how do you represent it? You see the general representation of the term. Okay, summation, the final term is the upper limit n, and here I is 1 or 0 you can say, and then the general expression for the, or the formula for the term is ri. This changes. Okay, it changes from 0 up to n. For this, the formula, this is pre-established formula, already established. This is the formula. How you show the proof for that? Now, this example I have included to show you another way of writing the proof using mathematical induction. In the first example, in your sum of integers, you were side by side, you were showing the steps for your whether left hand side is equal to right hand side or not. Here what you can do is that you consider only one side and you mathematically show it, you reach the right hand side. So you only deal with one side. For example, so this is the, this also, this is the sum of geometric sequence, and this is the notation for that. The formula is Rn plus 1 minus 1, R minus 1. So your first step will remain the same. Here initial value is 0. So it means that this is P of n. Now in basis step, what you have to do? What you have to show the proof of P of A. What is P of A over here? P of, look at the initial value, it is 0. This is what you have to show the proof of. So first base step and the assumption, that remains the same. Just in your proof, you are using a different technique. If you, I'll explain it to you from here. So this is P of A. Okay. And why you have plugged in 0 depends on the initial value. What you get the answer as 0 plus 1 is equal to R1. It means the same thing, R minus 1, and R minus 1 is 1. Okay. And your base step is same, 1 is equal to 1. The step that matters is K plus 1. Okay. So the steps that will differ in your second method is in P of K plus 1. So here what you do is that you take do you understand how you get this K plus 1 or no? This is simply, you had this, right? Then then in your assumption you will have K, right? And then in your proof you will have K plus 1. So it's simply that. Okay. So K plus 1 and everything else will remain the same. And this is what you have to show the proof of. And the formula is this: K plus 1 is K plus 2, and you get this. Now what you will do is that you will only, second method is you will focus on, you will take this left hand side and you will manipulate it in a way that you will reach here. So you are not dealing with both sides side by side equally. You are taking one side and you are using some mathematical methods to show it in this form. Okay, so that is why you need to know the knowledge of summation, product, and different types of sequences. Also the factorial, how to write down the recursive definition, and all that. So that will form your base to show the proof in different ways. So here what you can do is you can separate one term. The first term you can separate, just like in your factorial we separated this one is equal to, right? This is we studied just a few minutes ago. So what did you do? You just separated one term. Okay. So similarly what you will do is that when you are writing proof for this, you will simply separate the K plus 1 and you will write down the summation for your remaining values, means K up to 1. So for that, the summation you can take from your hypothesis, the inductive hypothesis. Okay, you can write down the expression for that and simply separate the r of k plus 1 value. Okay, and then from your assumption or from your inductive hypothesis, you know what this formula is equal to. What is it equal to? This one? Anybody? Are you getting what I am saying? Do you understand? Or no? Okay. Okay, let's say this is the sum of geometric sequence. Formula for that is it plus 1 or minus 1? Okay. Correct? Okay. And here, this is the initial value. Okay. So another way to show proof is your base step will remain the same. In base step, what you will do is you will take the smallest value, plug those in on both sides, prove those to be true. Left hand side equals to right hand side. Okay. I will not show that to you. It will be equal to 1. Okay. The difference is here in the induction step. Hypothesis will remain the same, which is assume inductive hypothesis, assume P of k, which is wherever you have n, replace it with k on both sides. Okay, this is your inductive hypothesis. This is important. Now, proving part will be different from the first example. In your first example, you manipulated both sides equally, okay? But in second example, it depends on the question, and it's up to you also. I am just teaching you different way of showing the proof. What you can do is that first write down it's a k plus 1 form. R k plus 1 is k plus 2. This. Now, what you can do is focus on this, take this left hand side and manipulate this summation to show it in this form, to reach here. Okay, so start from here, reach here. Don't touch this. Okay, this is another method. How? In this particular example, use your recursive definition for the factorial, that concept. What you have over here. This is the one that you have to manipulate. So in your factorial, we said that this is equal to, right? Correct? What we did over here? We simply separated the first value, right? So here what you can do is, you can separate k plus 1, keep everything else same as your okay. So you simply separated one value. Okay. Then what you, now from your inductive hypothesis, you know what this is equal to. This is equal to, this is from your inductive hypothesis. That is why I said mark it somewhere, okay? Mark it, this is important. You know that this is equal to this, right? So substitute it. And take this, bring this down as it is. And then you can make the denominator same. What do you get? Okay. when you simplify it, you will get the same answer as what you have over here. Okay, so you are starting from here, taking some steps, some mathematical steps, reaching this right hand side. Okay, so to summarize, in your first example, you are dealing with left hand side, both hand sides equally. In second example, you are starting from left hand side, you are reaching right hand side, taking some mathematical steps. Okay, that's up to you how you show. You just have to show that left hand side is equal to right hand side. First step is base step. They will remain the same for any statement. You have to show the base step. Second is you have to show the induction step. In your base step, what you have to consider, look at the question, initial value is given to you, plug in those values in your sequence left hand side, and in the explicit formula the right hand side, show that to be true. Only after you show the base step can you move forward, because if it is not true for the smallest value, how it can be true for any other arbitrarily chosen value. Okay, then assume the hypothesis to be true. That will be your inductive hypothesis. That will be the starting point of your proof. What you have to show the proof of k plus 1. Okay, so that is the summary. These general steps will remain the same, and within your proof, two steps will again remain the same. The inductive hypothesis, and second, replacing the sequence with the explicit formula from the inductive hypothesis. After that, it's up to you how you show that left hand side is equal to right hand side. Is it clear? So that is what mathematical induction is. And then lastly, you can use these two. I have given you two examples. So you can use these two formulas to deduce or create or develop additional formulas. Okay, they will form as a base. For example, let's go to the application of sum of first n integers, its formula, to find out a formula for another sequence. Here, let's say you are given this sequence 2 plus 4 plus 6 plus 500. This is sequence given to you. Now you can use the formula for first n integers over here, but you know that this is the formula, the first one that we solved. But you know that this formula is for sum of terms starting from 1, okay, up to n, right? Here, if you look at this sequence, so first you have to bring this sequence in this form. Okay, only then will you be able to apply this to evaluate this sequence or find a formula for that. So first analyze this sequence, see how you can convert it into this sum of first few integers, and then apply this formula. So how can you do that? You can take 2 common, this, okay, because you need to have 1, 2, 3, right? So here you see this is what type of sequence it is. The pattern shows you that it is sequence of sum of even integers, right? So to use the sum of first n integers formula, you first have to convert it into that. Okay, then you will identify the nth value, means the upper limit. Here this is the n, and after that you can apply, keep everything else will remain the same, means this, and now here you can apply this formula. N will be the last value, okay, the final term, and apply this formula over here. what will you get? Apply this formula. So you have n is 250. Then you have n plus 1. Yeah. And then you have 2. And this gets cancelled. So you are left with, so you can evaluate, you can find the answer for that. Okay. So this is how you can find the values, and also you can find out formula for some other sum given to you where you have final term in another form. For example, this one, I will show it to you. You have sum of first few integers, and your final term is h minus 1, and you have to write it in its closed form, means in its in the form of a formula. So here you don't need to do anything, just that here n will be equal to h minus 1, and you will simply apply the okay. So you'll apply this formula h minus 1, and this will give you n plus 1, h minus 1 plus 1 is, this gets cancelled, so you're left with h and 2. Okay, so you have this closed form of this sequence. So 1 plus 2 plus 3, from the sum of first n integers you can write down the formula for this sequence also, which is equal to h minus 1 into h by 2. Okay, so you can evaluate, you can find out the values for a given sequence, and also you can find out closed formulas, additional formulas using the sum of first n integers as a base. Okay, same applies to your geometric sequence. There also, you know that, let's look at one example of that also. For example, this one. Here, if you see 1 plus, first example, 1 plus 3 plus 3 square plus, this is your sum of geometric sequence, and you have to write this down in its closed form. So here you have everything. You just need to, the formula for geometric sequence is this. Okay. Here you will see what is the, this is the constant, which is the r. Okay, this we discussed when we were doing the proof for geometric sequence. And n over here is this power. Okay. So what you will do is that r will be this constant. So take that, substitute it, and then in place of n, take the power from the final term. Remaining formula of the geometric sequence remains the same. R is again substituted. This one. Simplify it. So this is the closed form for this sequence using the sum of explicit formula for sum of geometric sequence. Okay. All right. Clear? For second one, I think I have given the solution. Yeah, I have given it. So you can look at that, or I will just show you quickly. For the first one, now you see here something is missing. In order to apply the formula for sum of geometric sequence, you need to have the sequence, the values, the initial values and all those, you need to have those. Okay. So it means that you need to have 1, you need to have r. That is missing. So first you have to manipulate it. You have to analyze it and see how you can convert this into the sequence of, into geometric sequence for which this formula is there. Okay. Okay. Then after that you will apply the formula. So it's up to you. It's mathematical, you can say, creativity, or here if you see over here, if you take, for example, 3 to the power 2 common, what you are left with is, you need to have 1, right? So you are left with 1, right? In the second, what you are left with is what? Yes? 3, right? Because you know, when you have same base, when the base is same, you add their exponents. So you see here, 3 square into 3, 1 is equal to, what does it give you? 3, right? So you see 3 square, 3, 1. Then here what you are left with is 3. Yeah. And then 3 m minus 2. Okay. This will, when you add these exponents, it will give you the same as this. Okay. Now you have the geometric sequence, and now you can apply the formula over here. You know the final term means you know the n. This you will bring it down as it is, because this will be an explicit formula for this whole sequence, means this sequence. And here apply the formula r. R is what? This constant. Okay. So you can I will directly apply, substitute the values. Then final term is, means n is m minus 2 from here. Then from the formula you have plus 1, and everything else remains the same. You can simplify this. 9, 3 into 3 is 9, so 3 into m minus 2 is what? Minus 1, then this, and 2. So this is the closed form of this sequence. So first you have to, if the sequence given to you is not in, for example, in this case, it is not in the form of the original geometric sequence, first you have to convert it into geometric sequence. How you convert it? You have to find that out. You have to practice, okay? After you convert it, then look at the final value, means n. That you will find it from, for example, for geometric sequence, you will find that in the power of the constant, okay? Then you for geometric sequence, you need to know what r is. R is the constant, okay? So you see constant over here is constant real number, so that is here. So all these things, this is like prerequisite knowledge for your for using geometric sequence formula to find out formulas, explicit formulas for other sequences that are some like parts of or optimizations of geometric sequences, okay? Is it clear? No, not necessarily m minus 2. Depends. It depends on what are you taking common. What common? If you are taking common, what is the value that you are taking common? It depends on that. It's just like just like when you, for example, n factorial is equal to n into n minus 1 factorial, right? So it's the same thing, just you are writing it in different ways. So you keep your sequence, you know, when you multiply, you subtract, you add, the original sequence remains the same, okay? I will show you another example. This is in your algebra also. For example, when you break down two terms in some formula, a plus b square, there you divide the terms, right? But when you add them, you get the same. When you multiply, you get the same. It's the same thing. So yeah. Yeah, you have to convert it into the form for which that geometric sequence formula originally is. Otherwise, you will not be able to apply it. So you have to convert it into that form first. For example, if you have something additional, remove it from that sequence. If you have something, if something is missing, add that to the sequence. Okay. To show you an example of that is here, this one, part B, this one. You see, here you have to apply the formula for sum of first n integers, right? But you know that that sequence starts from 1, okay? And then up to n, right? So, but in this sequence, what is missing? These values are missing, right? Okay. So, you add them in a way, I will show it to you here. Where it is? Yeah, no, this one. So, you see, you added those here, but then you subtracted to keep the left and right hand side equal. Okay. Okay. So, and then you keep that in the body of your proof. For which you have to, the expression that you have to evaluate, or for which you have to write down the closed formula. Okay? So if there is something missing, you add it in a way that it doesn't change the overall sequence. If you have something, if there is a pattern which from where you can take common that will give you the original sequence, do that. Just like we took common here. We took 2 as common, so that gave you the original sequence for sum of first n integers. Okay, so that you have to analyze. Okay, clear? Okay, with this we will finish today's lecture, and let's mark your attendance first. If you have any questions, you can ask me. Please, all of you, mark your attendance. If you face any issue in marking your attendance, please come to me now. After the class, I will not respond to queries related to your attendance. Any questions, any issues with your attendance, come to me now. Any questions regarding your lecture, or also if you can stay for, we have 10 minutes, so let's discuss about your assignment also. I gathered the common questions that students sent me last week. Those who are going, please make sure that you get this information from your friends. So for your assignment, there were a few queries related to dataset and what else was there? What you have to include and how you have to write that down. So dataset, the sources that are given to you are just to guide you. If you don't find dataset from those sources, you can use any other source, but you have to provide reference. Okay? You have to provide the reference of the source from where you are taking the data. If you are unable to find the data set, for example, those who have case study related to medical facilities, if you are unable to find it online, you can look into the physical facilities around where you are living, and you can look into clinics, hospitals. It's not necessary that there must be hospitals. It's not necessary that there must be clinics. They could be any medical facility. If you don't find it online, you can look into those facilities around you in the area scope you will define. Whether you are covering a town in Malaysia, a city in Malaysia, a rural area in Malaysia, any other country, it's up to you. Just that you have to define the scope in the content. You have to explain everything in the content. Then one example is that maybe you will find 10 to 20 hospitals or clinics around you. Look into just go and search for the websites. From there you will be able to find the columns that you need for your to complete the task. So you can use that. You can create data set from there. All of your data should not be synthetic. It should not be imaginary. You should have at least some data that you have taken from somewhere that has been collected, or you collected from the physical facilities. Okay, and then if you find it to be less comprehensive, you can add to it based on the patterns you find in the data set that you have already found. Okay, and explain that in the content. Okay. Whatever you do, explain that in the content of your task, in the body of your work. Okay, and another thing, each task you have the application of certain discrete structures, concepts, their application in real life domain. So each task is actually a problem domain, and you are when you are answering the question, you are actually proposing a solution or recommending a solution. Okay, so for example, you have to apply some concept from set operations. You have to apply some concept from counting, like permutations and combinations, from your graph theory. You are free to choose, for example, from graph theory, you are free to choose the algorithm, for example, to find out minimum spanning tree. There are different algorithms. One example that is given to you in that in the guidelines is there is one algorithm given to you, but it's not compulsory. It's not necessary that you must use that algorithm. There are other algorithms also, like Kruskal's algorithm, Prim's algorithm. You can use any algorithm as long as it suits with the answer of your task. Okay, explain it. Dataset also explain it. How much data you have, what limitations were there, what difficulties you faced. Okay, what are the limitations, define the scope, everything. That freedom you have. Okay, so you don't need, for example, set operations. Yes, you have to use the concept from set operations. For example, union, intersection, whichever you use, it's up to you. Whichever is suitable with your answer, whichever gives comprehensive answer. So, and then justify that why you have selected that particular set operation. Okay. You can use union, you can use intersection, you can use any other set operation, you can use both, you can use one. It's up to you. It falls in the category of critical thinking, creativity, and comprehensiveness of your answer. Okay, so you are free to choose. You have freedom to choose the concepts within the main topics. You have the freedom to choose the data set which is suitable with the task. Okay. And also you are free to choose any source of the data set. It's not necessary that you have to use only those 3 sources. All right. Another thing was about can you copy paste the cover page? Yes, that is for you to copy and paste it in your report. Copy the cover page, paste it in your report. Second assignment task table is given to you on the under this group assignment section. That will be your second page. This one, I will show it to you. If you go to second one, assignment tasks table, this you have to include as a second page, because we will use this table as a reference when we conduct Q&A session. So you have 4 tasks. Whether you completely do a task or you partly do a task, just check, okay, tick mark which task you have done. Because we will refer to that and we will see, okay, this student has done this task, so we will ask specific questions based from that task, from that student. We will ask 2 types of questions, one generally about the project and second will be specific. So we will refer to this table. Q&A session will be individual for each student, okay, marking. This will be your second page. Then make sure that you include, and also while working you refer to your marking rubric, okay. First page, second page your table, third page will be in your first page you have to copy paste the title of whatever case study you are given. All that is given to you in the case studies. For example, you are given assigned case study 1, just copy this title and paste it in your cover page. Then third page, here you will starting from the third page you will answer the questions included in your tasks. Each task on a separate page, okay. Then refer to, after you are done with the task 4, you will have your list of references, okay, after task 4. Then after that you will have your marking rubric. Here is your marking rubric. This is your marking rubric, just copy paste it. Refer to this criteria. Make sure that you know this criteria. This is the criteria that we will assess you on, and then for your Q&A session also, okay. So copy paste this one after list of references, and after that your complete Turnitin report, similarity report, complete report, okay, not screenshot of only the percentage, complete report that you will generate from here. Here I have provided a link. Here you see Turnitin similarity and report generation. So you will, once you are done with your report, upload it over here to check the similarity. Then look at the overall percentage of similarity that is allowed. So that is 20% overall, and from each single source it's 2%. So check in your report will tell you from each source how much content is similar, and overall percentage will also give you, okay. First 3 times when you upload, you will get your report instantly. After 3rd time, your report will be generated after 24 hours. So make sure that you have this much time, okay. So if you want to make any adjustment, you can make, okay. And another thing is about refer to the submission criteria, because you have this in your marking rubric also. So this one, please stick to this these submission requirements. Your formatting and full report, one document, please go through it. Go through the submission criteria, go through the marking rubric, and I have told you where the places where you have the freedom to choose what you can do and what you cannot do, and also submission dates. Please keep these in mind, okay. Is it clear? Midterm will be in week 9, lecture hall. Most probably lecture hall.